In this video, we will discuss on hydraulic turbines. The major outlines are hydraulic turbine, hydraulic power, hydroelectric power plant, classification of turbines. So, we will discuss one by one. Now, what is hydraulic turbine? You know that in hydroelectric power plant, hydraulic turbine is the main machine which converts the hydraulic energy into mechanical energy, and this mechanical energy is utilized in the generator to run the generator to produce the electrical energy, and this is the overall known as the hydroelectric energy. So here hydraulic machine uses the energy of flowing water, and how this flowing water comes, you know that in hydroelectric power plants we have the setup for dam, and from the dam water is flowing, and that flowing water, and we can say the water possesses the potential energy, and that potential energy is converted into kinetic energy, and that water with kinetic energy comes to the hydro power plant where turbine setup is there, and that runs the turbine, and with the help of the kinetic energy turbine runs and the mechanical power develops. And here it is mentioned that the energy that we are getting as the output, it is in the form of rotation of runner. What is that runner? In turbine there is a rotary part of the turbine which houses the number of vanes in series, and those vanes carry the water. When the water injects on the vanes rotate, and that rotation of the vanes uh, results into the rotation of the runner. One thing, so this is the small definition where you can see how the energy conversion takes place in the hydraulic turbine. That is, the hydraulic energy means the energy present in the flowing water converted into the mechanical energy. Next, we will discuss that what is that hydraulic power that we want to generate in the hydroelectric power plant. So, to develop this hydraulic power, first thing we need a turbine, and as you know, turbine is a machine. What kind of machine? It is the hydraulic machine. So this particularly this hydraulic machine is rotary one. Rotary means when force will be given to this turbine, it will rotate. So this is rotary one. So here we are applying the we are supplying the water, and that water is flowing into the turbine with potential energy or kinetic energy. In case of some turbine, the total energy is kinetic energy, but in case of other turbines, we found some energy in the form of potential energy plus kinetic energy. So when we give energy to the turbine by means of flowing water, turbine rotates, and when the turbine rotates, its shaft rotates. So here I have shown the rotation of the shaft, and I have written here ME, that is the mechanical energy. Turbine produces the mechanical energy, and that mechanical energy is utilized in the generator. And generator, and you know, generator produces electrical energy by utilizing the mechanical energy from the turbine. That's why turbine is known as the prime mover. So this is the prime mover for the generator. So this is the basic concept how we get this hydraulic power, and the conversion of mechanical energy into the electrical energy combinedly gives us the hydraulic power, and that we obtain in the hydroelectric power plant. So what is that hydroelectric power plant? We will discuss. This is the general setup for a hydroelectric power plant. In Odisha, you know, in Hirakud, there is a hydroelectric power plant where we use the turbine, and the entire setup is there where power is produced, and that kind of power is known as the hydroelectric power. and you know that what is the importance of electricity day to day life. And we are producing electricity in major part in case of thermal power plant. In secondly, we are using the hydroelectric power plant to produce that electricity. So this is the second major power source in India by which we are getting the electricity. Now, what is the layout of this hydraulic power plant? You can see generally in case of the hydraulic power plants, there is a setup for the dam. That means there is a reservoir where water is get storage, and that stored water is supplied to the powerhouse. What is that powerhouse? It is the assembly of turbine generator, and this turbine generator assembly is producing the electricity, and that electricity is again gone through the proper channel, that from the transformer, then the transmission line, then distribution, and electricity is distributed. But our focus is where is the turbine, and this is the setup for the turbine. How this turbine runs? When water flowing from high head and coming into the turbine, the energy present in the water, known as the hydraulic energy, is utilized to run this turbine. And after the starting of this turbine, we get the mechanical energy, and that mechanical energy is utilized in the generator. Already we have discussed on that. So this is the setup for hydroelectric power plant. So we will focus on this turbine and not all those things. So what is that turbine? What are its classification? This is the point of discuss. Now we will discuss about the classification of the turbine. Very first point in the classification part, if we will consider the energy at the inlet of the turbine, turbines are classified into two types. One is the impulse turbine and second one is the reaction turbine. What is that impulse turbine? What is that reaction turbine? We don't know. First thing, energy at the inlet. You can see it is a turbine, and just I am taking this is a turbine, and when water is flowing into the turbine, suppose water is flowing like this. When water is flowing into the turbine, what is the energy present in the water? That energy, we can say that energy is the hydraulic energy. But when this water is coming to the turbine, if it is totally kinetic energy, then we can say this is the impulse turbine. If some of the energy converted into kinetic energy and the total energy is the combination of potential energy and kinetic energy, you can say the pressure energy and kinetic energy, then this type of turbine is considered as reaction turbine. So what is that? Totally it depends upon the energy at the inlet. So if it is the energy present in water is totally converted into kinetic energy, then we will consider that as impulse turbine. Or second case, if it is partly pressure energy, partly kinetic energy, then it is considered as reaction turbine. So later we will discuss briefly on that. And now we will see what is that impulse turbine and what is that reaction turbine. In the first figure, this one, simply we can say this is the runner. Already we discussed about that. There is a rotation of runner, and due to this rotation of runner we got this mechanical energy. So here is the runner. To run this runner, there are the series of vanes. You can say these are the vanes or buckets, and water, or you can say jet of water. Jet of water is directly coming out from the nozzle and striking the buckets, where due to the for this the bucket starts revolving, and due to that we get this rotation, and due to this rotation the runner rotates. And when the runner will rotate, here is the, you can see, here is the shaft. When this runner rotates, this shaft will rotate, and due to the rotation of shaft, we will get the shaft power, and that shaft power is utilized in the uh, as the main power source for the generator to run the generator. Here, the water is directly flowing towards the vane, and kinetic energy is present in the jet of water, not pressure energy. Pressure always remains constant in case of the impulse turbine. There is no variation of pressure. Pressure is constant, but the kinetic energy, the total energy, is the kinetic energy. Next case, if we will consider the reaction turbine. Here, mostly the reaction turbines are the radial flow or axial flow turbines. Here, water, the direction of water is here, you can see, and when this runner or rotor will rotate, then will obtain that rotational energy, or you can say that is the short power. But in case of reaction turbine, the energy at the inlet is partly pressure energy and kinetic energy. Okay, so in case of impulse turbine, we use the nozzle, and by utilizing the nozzle, we convert the energy of water into kinetic energy. But in case of reaction turbine, nozzle is absent. So water directly come into the guide vanes, then the vanes, so that in the absence of nozzle, there is not 100% conversion. So we obtain partly pressure energy and kinetic energy, and this is due to the reaction pressure in the reaction turbine. So this is the basic difference between the reaction turbine and impulse turbine. Next, we'll see another mode of classification. What is that? The according to the direction of flow through the runner. One thing, in the hydraulic turbines, there is special type of runner arrangements, and depending upon those arrangements, the flow of water is also changed, and according to the different types of flow of water to the runner, these are classified into four types. The first one is the tangential flow turbine, second one is the radial flow turbine, third one axial flow turbine, and the fourth one is the mixed flow turbine. So what are these turbines? We will see one by one. In the first case, this is the tangential flow turbine. Here is a picture. This picture is showing that this one is the rotor or runner of the impulse turbine. These are the series of vanes which are mounted on the runner at equal distance. This one is the nozzle from where the jet of water is coming out, and when this water comes out from the nozzle, it directly hits the vanes or buckets, so that there is a conversion of hydraulic energy into mechanical energy. So in this case, particularly when the water strikes, particularly in this case, when the water strikes, what happens? The bucket is like this. When water strikes, this is the direction of flow of water, and this is not water, this is jet of water. When water strikes at this point, it exits like this, and this is the simple direction of flow of water in the bucket, and depending on this, we can say this is the tangential flow turbine. So the best example for this tangential flow turbine is Pelton wheel. So this Pelton wheel is the example of tangential flow turbine. Depending upon what? Depending upon the direction of flow of water. Next case, secondly, this is axial flow turbine. What is that axial flow turbine? We will discuss. Here, this one is the axial turbine, and we can say this one is the axial turbine. This line indicates the shaft. When water enters into the turbine, it enters axially. When water exits the turbine, it exits axially. That means the arrangement of the turbine, depending like just I am showing. This is the conditions suppose. These are the we will discuss later. This one is the arrangement of the hob where the number of bands are fixed. When water comes into the turbine, it enters axially, and water exits the turbine axially. That's why this is the axial flow turbine. This is one type of arrangement, and the example for this type of turbine is Kaplan turbine. In case of propeller turbine also this type of arrangement is there, and in case of Kaplan and propeller turbine we see this axial flow of water. Next one is the radial flow turbine. Why it is known as radial flow? Because the water enters the shaft radially. How? Here this is the layout of the turbine. Water enters radially in and here it is radially out. How you will understand this concept? What is that radial flow turbine? Simply suppose the shaft and rotor is there, and on the rotor suppose I am taking one van. This one is the single bucket. Water enters the bucket like this. That means this is the radial direction to the axis of the shaft. That's why this type of turbine is known as radial flow turbine. If you will see the arrangements in radial flow turbine, the buckets will be arranged like that. So water will enter radially in and water will exit radially out. That's why this is known as the radial flow turbine. And the last one known as the mixed flow turbine. Initially what has happened, the radial flow turbines are there. The best example of radial flow turbine was Francis turbine, but due to some problem that is modified, and the modification version of that Francis turbine has come, and that one is known as the modern Francis turbine. That modern Francis turbine utilizes the mixed flow of water. What is that mixed flow? This is not radial water and exit radially. So the flow of water to the turbine is axial. That means in the direction of shaft, but water will exit in the radial direction. That's why it is known as the mixed flow turbine. The example is modern Francis turbine. Next one. This is another mode of classification where we will discuss the classification according to the head. What is that head? First we will discuss. In case of hydroelectric power plants, what happens? There is a fixed position for turbine, but there is a level, upper level for water. That means you can say this is dam or whatever, where this is the storage device, storage place where water is stored. When water is released from the dam, it comes to the turbine through the penstock. So penstock carries water from the dam to the turbine, and if you will see, if this is the datum level, if this is the datum level and this is the total upper level of the water, the difference between these two level is known as the head. That means we know that if head is very high, then the potential energy is very high. If head is low, then potential energy is low, and that potential energy is converted into kinetic energy. Already we have discussed. That means in case of turbine, we convert the potential energy into the kinetic energy. Potential very high kinetic energy. So in there are different setups in case of the tangential Pelton turbine, in case of the Francis turbine, for the Kaplan turbine, we use different heads. Mostly the Pelton turbine is a high head turbine, Francis turbine is the medium head turbine, and Kaplan turbine is the low head turbine. But according to that, this difference of height from the upper level to the datum level varies. In case of Pelton turbine, it is very high, more than 300 meter, and in case of Francis, it is in the medium range. In case of the Kaplan turbine, it is very less than 30 meters. So depending upon this difference, the energy conversion also varies. So this is one kind of example. We can see according to the head, the turbines are classified into three types. One is the high head turbine, example Pelton turbine. Second one is the medium head turbine, that is example Francis turbine. Third one is the low head turbine, example Kaplan turbine. Next, this is the range. You can see for high head turbine, the range is greater than 300 meter. That is, in case of Pelton wheel, the head is greater than 300 meter. So that's why we obtain more and more kinetic energy in case of the Pelton wheel. That is, there is a huge conversion of potential energy into kinetic energy. In case of medium head turbine, in case of medium turbine means that is the Francis turbine. What happens? The range is 60 to 300. Most probably 150, 180, these heads are used in case of Francis turbine. And next one is the low head turbine. In case of the Kaplan turbine, what happens? The head is less than 60 meter. So in case of the different heads, we have to vary the discharge. So what is will be the discharge in case of the three turbines? If the head is very high, the discharge will be low, first point. If the head is within the range of 60 to 300, then discharge will be in the medium range. Then if the head is less than 60, 10 to 30 whatever, then we need huge quantity of water, as in case of the Kaplan turbine. So for this case, very less water is required as the head is very high. In the last case, huge quantity of water is required because it is supplied at a very low head, and in the medium range the level supply of water is optimum. Next, we'll see another mode of classification. It depends upon the specific speed, and depending upon the specific speed, the turbines are classified into three categories. First one is the high specific speed turbine or high speed turbine. Second one is the medium speed turbine, and third one is the low speed turbine. And what is that specific speed? You can see this is the speed of a geometrically similar turbine that produce 1 kilowatt of power per unit head. That means if you utilize 1 unit of head of water, how much energy we will obtain from the turbine? we will exactly obtain 1 kilowatt power, and that is known as the specific speed. And depending upon that, the turbines are classified into three categories, and we can see the range of specific speed. For the low specific speed turbine, the range is 10 to 50 rpm, then second one 50 to 350, then third one is 250 to 850. What happens, this range is up to 250, 300 to 1000. And this is the close overview of all the three turbines. The first one, here I have written Pelton wheel, second one Francis, third one Kaplan. So I have categorized three turbines. What is that Pelton wheel turbine? This is impulse type. Already we have discussed, in case of impulse turbine, the energy at the inlet is totally kinetic energy. Francis turbine is the reaction type, that means the energy at the inlet is totally pressure energy and kinetic energy. This is the combination. Kaplan turbine is also the reaction turbine, energy at the inlet is pressure energy and kinetic energy. Now this Pelton wheel is tangential, this Francis turbine is radial or mixed type, and the Kaplan one is axial. Depending on the head, Pelton wheel is high head turbine, and Francis is medium, and Kaplan is low head turbine. As head is high, medium, low, its discharge varies accordingly, so that if it is high head turbine, its discharge will be low. If it is medium head, discharge will be medium. If it is low head turbine, discharge will be high. And this is the range of the specific speed. Overall, we can say that the turbine is a hydraulic machine which converts the mechanical energy, which converts the hydraulic energy into mechanical energy. That mechanical energy in terms of rotation of the runner, and that mechanical energy is utilized in case of the uh, generator to produce the electricity, and that gives us the hydro electric energy.